But okay, the main topic here is constructing Euclidean quantum field theories from SPDE theory, okay? So I'll define precisely what a Euclidean quantum field theory is, but I believe some people in this audience care a lot about quantum field theory. And so this program of Euclidean quantum field theory started maybe in like the 70s, roughly, around that time period. And there was this idea where you can construct rigorously these quantum field theories using probability theory and PDE theory. And they were able to construct a few quantum field theories quite rigorously, but it was very, very, very hard work. And eventually they got stuck doing harder things. And the field maybe sort of died like 30 years ago, maybe, arguably. Most certainly yes, though. Okay. But now this field's kind of coming back to life a little bit back in the probability world because of some application of SPDE theory to this construction of Euclidean quantum field theory. So the end of the talk, the last like 5-10 minutes, I will introduce SPDEs and this tool of stochastic quantization, which uses SPDE theory to construct these. But the majority of the talk will kind of be on the setup of Euclidean quantum field theories, how it might be related to the quantum field theories you're used to, etc. But okay, talk outline. So maybe the rough outline. So I'll just start with like doing quantum mechanics, okay? And then I'll do some Euclidean quantum mechanics, okay? I'll explain how to go back and forth between these two things. So there's this operation called a Wick rotation. Okay, some of you may or may not have seen this before, but it'll be hopefully a good review for those of you that have. And I'll give you an example. I'll do kind of a simple harmonic oscillator, which is like one of the most canonical quantum mechanical systems there is. And I'll go back and forth between this and the Ornstein-Uhlenbeck process, OEU process. So this will be some kind of random variable, and this will be some kind of quantum system. I'll explain how to go back and forth between these two. Okay. I'll also, still on this QM, EQM world, I'll describe what it means to do like a Gibbsian perturbation of some Euclidean quantum mechanic data. Basically, this is like a little quick tool that you can use to construct more Euclidean quantum mechanics from one that you already know, okay? And this will inspire stuff when I go into the quantum field theory world. So I'll do very briefly kind of what changes when you do from QM, EQM to quantum field theory and Euclidean quantum field theory. Now, I'm not so much of an expert on quantum field theory, so I'll keep this side a little bit brief, but I want to very precisely define what this Euclidean quantum field theory is. So in particular, I'll do the definition of Euclidean quantum field theories. I'll give you kind of the canonical example, which will be the Gaussian free field with mass m. Okay. And then I'll talk about one of the most simplest perturbations you can do of this Gaussian free field, which is going to be the 5-4-3 model. Okay? 5-4-3 model. And this is given by a Gibbsian perturbation of my Gaussian free field, okay? And then maybe the last little bit of my talk, so 1, 2, and then 3, this is going to be this new technique, stochastic quantization, which is sort of a new technique, for these kind of Gibbsian perturbations, okay? And this uses SPDE theory, which I don't want to get too much into, but I'll write a few SPDEs and we'll pretend we understand them together, okay? For Gaussian perturbations. Okay, all right, sounds good. All right, let's do some quantum mechanics. Okay, so in quantum mechanics, I'll always have myself a Hilbert space. H is my Hilbert space. And this will be made out of my states omega, which will be my states here. In addition, I'll have my algebra of operators. So this is going to be operators, which is going to be kind of I guess functions, perhaps bounded continuous functions on my Hilbert space that are going to be self-adjoint. Okay, and then now my states can act on my operators via the measurement like this. So a state omega acts on an operator A via this inner product, this Hilbert space inner product. So omega A omega. Okay. Okay. In addition, I can think of this. Okay. So far so good. Now in quantum mechanics, I have a kind of a time evolution operator. So U of t. This is my time. It's kind of like a unitary time evolution operator. Okay. So at every t, it's going to give me a different unitary operator. And these U of t's, they act on operators in the following way. So if we have A, some operator A, and at time t, all this is given by given by conjugating by my matrix U. A U of t. Something like this, okay? And then again, I can either think of evolving my observables, which is what you call a Heisenberg picture. Heisenberg picture. Okay, or I can think of evolving my states, omega of t, just by multiplying by my unitary matrix. Okay, so this is the Schrodinger picture. And in fact, they're equivalent. So maybe I'll put a little bit. So on the bottom of this board, you can see quickly that if I look at W of t, apply it to A. Okay, this is equal to W of t, A W of t, which is equal to U of t W, A U of t W, and then I can move the adjoint of U is going to be its inverse. So I can move this other side. This is going to be W U of t inverse A U of t W, and this is just equal to W acting on the matrix A of t. Okay, so it's equivalent. I can evolve either which way I want. Okay. So I'm going to make a few assumptions on my quantum mechanical data. So in particular, I'm going to want to have a ground state. And I'm going to want this ground state to be cyclic. So what do I mean by this? Okay, so assumption, very, very key, is that there's going to be a, let's see, there's going to be a cyclic ground state or vacuum state. Okay, so this is going to be a very special state, omega. So it has two properties. One is that if I time evolve omega, I'll get back omega. Okay, so it's very under time. And two is that I can kind of get to any other state from omega by hitting it with some other operator. So meaning that for any kind of V in my Hilbert space, there exists some operator A such that V equals A of W. Okay. So in this sense, this is cyclic here. Okay. And now with these assumptions, my entire Hilbert space structure can be captured by looking at these things called Whiteman functions. So let's say W, let's see, it can evaluate times T1 through Tn minus 1. It'll take in operators A1 through AN. Okay, so I take n minus 1 times in A operators. So I'm going to call this my Whiteman function. Okay, and what this is this is just going to be W, and there's going to be A of T1, A of T2, all the way to A of Tn back to my omega. Okay, and now because this is cyclic, I kind of know all of my Hilbert space structure just by knowing what these values are for any sequence of operators A and for any sequence of times T. Okay. Now I can also write this using my time evolution U here. So this is going to equal W. It's going to be like A T1 U of T2. I guess it's going to be A1 It's going to be u of t1, a2, u of t2 minus t1, all the way to an w as well, okay?
If A is that A1 and T1?
Yes, thank you. A1, A2, an, my bad, yeah.
So there's the n minus 1 times.
Sorry. Yeah, sorry. It's a good point. I should, okay. For now, let me define this as Tn. But the reason why I wrote it originally as n minus 1 is because of these time evolution operators here. I only really need to know the gaps between T1 and Ti and Ti plus 1, because when the last time hits W, it's invariant. So I really only need to know the gaps of these guys here. But I might go between writing T's and the gaps of T's occasionally. But okay, really, I understand my Whiteman functions if I know my time evolution operator is U, okay? So now let's try to go into Euclidean world. So let's go from quantum mechanics to Euclidean quantum mechanics. And the idea is pretty simple. Instead of doing quantum mechanics in time t, I'll do quantum mechanics in time it. So I'll make my time imaginary. Okay, so I switch from t and I go to it. What this means, okay, instead of looking at u, I'm going to look at another operator, k of t, which is equal to u of it. Okay. And instead of looking at these Whiteman functions, I'm going to look at these Schwinger functions. So now I'm going to have Schwinger functions. And it's going to be the exact same thing, but with k's instead of u's here. So it'll be like k of, I guess, same kind of input. I'll write t1, tn, a1, an. Okay, and it'll be, I state w, it'll be a1 k of t1 all the way to k of tn minus 1, an w. Okay. Now, when I first write this, you might ask, what's the point, right? Like what is the advantage of doing this? I haven't really changed the problem too much at this point, but there actually is a very key advantage. And that often, if you're lucky, in fact, often you can do this. This k of t, this is going to correspond to the semi-group, I'll define this in a little bit, of some random process xt, okay? So xt is going to be some kind of random function on all of R, okay? And k I can get from xt in a way that I'll describe in a little bit. And these Schwinger functions, I can write these in terms of correlation functions. Of my process xt, okay? So what do I mean? So let's go, I'll give you like a rough heuristic example, roughly explain why it makes sense, and I'll go to a more concrete example after. Let's see. Okay, so back to Euclidean quantum mechanics. So if you're lucky, if you define everything correctly, if you define the process xt in the way that you should, which I'll be a little bit vague on how you should do it, but this k with this exact same input here, it's going to exactly correspond to, take an expected value, you look at your process x at time t1, you're going to evaluate a1 here, you're going to evaluate a2 at time xt2, and you look at evaluate an at time xtn, okay? Maybe as an example, where, I guess in this example, I can think of my a's as just being continuous functions on R. These will be my operators. And so a just given by some kind of function and just evaluate at x of ti here, okay? So if you define everything correctly, these equalities should be true. How do you see this? Well, let me do a really simple example. So I guess I'm a basic calculation. If I look at a of, let's say I have a1 actually, I should say first, I should define how to get k from x. So the way you define k is, define k as, so k is going to be operator. It'll act on functions f. And the way I evaluate this function x is I look at the expected value of my function evaluated at time t in my process, and I'm going to assume that my process at time 0 is given my little x, okay? So a little bit to unpack here, but again, xt is going to be some kind of random curve here. Its distribution, hopefully I can write down. And then let's say at time 0, I'm equal to x here, okay? So now I look at this conditional distribution, okay? And now when I look at this conditional distribution, I can write down, if this is time t over here, I have some kind of distribution for x at time t. And then I can kind of compute this expected value using the known distribution of x at time t, given x at time 0, okay? If there's any confusions, please feel free to ask. But this is how I define the, I guess, the semi-group of my process here. And also maybe one quick thing to check as well. If I look at k of f and evaluate at like a delta function, like delta sub y, okay? So this is like a delta spike here. What this will give me is this is going to be kind of like my transition probabilities of my process from going from x to y, which is, I'll write more heuristically, the probability that xt goes from x to y in time t. Okay, so in this kind of way, this k sort of just captures the distribution of x. Yes.
The right-hand side depends on something.
Yes. Yes. So there's another t there. Thank you. Okay. So now let me kind of motivate this reasoning. Another question? Oh, f is any function or operator. So f again is some kind of operator. Maybe I called them like big A earlier, but again, it's just a continuous function R. Okay. Because yeah, I could have written A. I guess maybe that would be more clear. Maybe it's the same thing if I wrote an A, but I can also write F, for example. And maybe I'll go back to F for a second. Very good questions. Any more? Yes. Yes, thank you. Okay. Looks good? Yeah, so this is a really good point, actually. So, often when I'm on the Euclidean side, I'll start with a random process X. I don't have a Hilbert space yet. I need to construct a Hilbert space. So in this kind of weak rotation backwards, I'll need to pick my Hilbert space in the correct way, or going kind of the other direction, I need to pick the distribution xt, and as well as like how I basically need to pick the distribution of xt so that something will correspond to the Hilbert space to start off with. It'll be maybe a little bit more clear in my example. I'll give in a second. But this is actually a very good point. So let's go back to.
What told you to pick
Oh yeah, this is just a basic example. Yeah, so yeah, exactly. Okay, so maybe if we look at the expected value of A1 at x at value at time 0 and A2 value at x at time t. Okay, well, I'm going to do some conditioning here. So this first line, it might not make sense immediately, but hopefully it'll make sense after I explain it. Okay, so I'll write the same thing here, A1 x1, A2 xt. And I'm gonna condition on the values of x of s for time s less than or equal to 0, okay? So what this means is I'm gonna first assume I know everything for all negative time and also time 0. Then I'll do some conditioning or expectation or averaging here. And at the very end, I'll average everything as well, okay? So I'm kind of, this is sort of like a Fubini theorem, where I first average out, assuming I fix these quantities, and then I average out everything else, okay? And now, because this quantity here is exactly known if I know the values of xs, okay, then from here, I can pull this out, and I have a1 x naught times the expected value of a2 of xt given xs at s less than or equal to 0, okay? Now, from here, I actually will impose some extra necessary assumptions as well. So I'll do a additional assumption. Which I'll roughly explain in a second. So I'm going to basically assume in this example, at least, that my process X is Markovian. What do I mean by that? Well, I mean just that conditioning for all negative times is going to be the same just as conditioning at time s equals 0. Okay, so this is kind of like saying my process X is memoryless. So if I knew the infinite past, that's the same as just knowing my current position. Okay? So I'll write something like this: expected value of a1 of x naught times this conditional expectation, a2 of xt, given just x0. And then from here, now my k comes in here. So this quantity here is exactly equal to the expected value of a1 of x naught. And this here is exactly kt evaluated at a2, all about evaluated at x naught, okay? Okay. Now, from here, I need to explain a little bit where the Hilbert space is going to come from. So let's say x naught has some kind of law on mu here, okay? Okay, this is going to be some law on real numbers here. So this quantity here, if I integrate this, this is going to be like integrating a1 some little x, kt a2 a little x, and then d mu of x. So I kind of integrate the law of my function at time 0, okay? And then from here, this is exactly, if I define my x correctly, this is going to be my, given by my Hilbert space inner product. So a1 at my state x, and then k2, a2, say kt, a2 of x, okay? Where what I'm doing here is I've picked my mu in such a way so that my Hilbert space is going to be kind of L2, it's going to be R, and it's going to be d mu of x, okay? So I've kind of gone backwards a little bit here. Really, I would have started off with this Hilbert space, and then I would have picked this x so that its distribution at any particular time is given by this mu here, okay? But once I have this is given by my Hilbert space quantity, and now the a's, I mentioned at the very beginning as self-adjoint, so then I can move the a1 to the other side. So let me see. Fortunately, I didn't give myself a lot of room, but okay, so this is equal to star, and then star, so this is kind of, which is also equal to this. This is just equal to my Hilbert space, x, so this is my state, my ground state, a1 kt, a2 of x. And this is kind of my Schwinger function evaluated at time t and the operators a1, a2. Okay. Yeah, so I need to pick the ground state in such a way so that this integral here corresponds to my initial inner product. So it's kind of picked in the right way. Okay.
Sorry.
Yeah.
So these two boards, I need to understand the logic and what is going on.
Yeah, for sure.
So
Okay.
I don't know, for example, this is an example. So you explained the formalism before, and this is now an example. In
Yeah.
what sense is this an example? Are you telling us?
So I guess I've restricted my Hilbert space to be given by maybe some L2 space.
Yeah.
And my operators to be kind of continuous functions. Okay. And so in this example here.
So you've also fixed. So instead of providing U of t,
Yeah.
K of t, you're providing a random process.
Yeah. So exactly. I'm defining.
What kind of process is this?
Yeah. So.
What are you assuming about the process? What is its domain? What are the values it can take, etc.?
Yeah. So x. This is a good question. So xt for any particular t, it's just going to be an element of R. Okay. So there's a entire process for t and R, All this is that in any particular instantiation, this is just going to be a continuous function on R. Okay? That's all I'm going to assume. And then from xt, I can define this kernel k, kt here, okay? And then
XT could be, for example, a random walk on the real line.
yeah. Or it can be a Brownian motion, or and it can be many different things. And I'll give you a much more concrete example in a second, which will have a very concrete example of xt. And from there, hopefully it'll be more clear. But again, I have xt, a process. From there, I make my kt, okay? And then assuming that I pick the law of this correctly, okay? This kt is going to correspond exactly to u of it. So that means once I have this kt, well, I can construct the Schwinger functions. These guys over here. So originally I defined Schwinger functions via Hilbert inner product. But if I define my process xt correctly, this is also given just exactly by correlation functions of my process xt. So just by knowing the correlation functions of my process xt, I now know the Schwinger functions. And now to go from Schwinger functions to back to my Whiteman functions, so back to my quantum mechanical world, I want to, in a second, I'll analytically continue this time. So I'll go from t to it, so kind of going backwards. And then I'll arrive at a Hilbert space with a unitary operator that is time translations.
Okay, but I'm trying to understand, so what is this computation that you're doing? What are you trying to demonstrate?
Yeah, so here I'm kind of just sort of demonstrating that for some kind of process xt, quantities like this can be written by a Hilbert space inner product of this form, where the Hilbert space is given by something of this nature, right? So this is sort of the way to go from correlation functions to Hilbert space inner products. Right?
It's important to point out that not every U has a K which can be represented.
Yeah. You got to be a little bit. You got to pick your U's correctly. There will be.
Well, I mean, I didn't ask about you.
Yeah.
You didn't even say that it was a one parameter group.
Oh, I should say it's one parameter unitary group. Yes.
Yeah. And then you want, after Wick rotation, for this thing to give you something like random walks, etc.
Yeah, or the semi group for a random walk or something like this.
And so this is like a probabilistic way of rephrasing.
Yeah.
The Feynman path integral. You're basically describing the Feynman path integral expression for expectation value.
Yeah, using correlation functions. Yeah, exactly. Okay, so this example is a little bit vague, so I want to be a little bit more specific now. So now I'm going to talk about a particular random process.
Could you explain the first equality, please?
Yes. Sorry. It's
on the right board.
On the right board. Here. This. Okay. So all I've done is Fubini's theorem. So, okay. So, yeah, this is a good point. Okay. So let's say instead of having, so maybe if I have some kind of function f, and I evaluate at time x positive and x negative. So this is a very formal one I'm going to write here. Okay. Okay. So think of, can you see the board over here? Okay. So the x positive, roughly what I mean by this is I mean all positive times in my process. X negative is going to be all the negative times in my process. And I can choose to integrate all the positive times first and all the negative times first. Okay. So kind of if I do Fubini theorem in this way, it's kind of like I fixed my x negatives. So I assume that all my x negatives are just fixed numbers. And then given these x negatives, now I integrate out or do an expectation over all the positive times. How does that feel?
Why does the expectation involve integrating all times? Because it only has a fixed time. It's like E of x sub t.
Over the expectation of the entire process here. And I have two times, 0 and t here.
So then why does it involve integration over all times?
So really, the law of xt, okay, there's a few ways. So really x0 and xt live in a much bigger probability space, which has xt for all time in R, right? So I kind of want to go back to my much bigger probability space, and then I do some conditioning on the bigger probability space. Essentially, I do Fubini's theorem on the bigger probability space, and that shortens the calculations, and I end up back to something that I can use here. Okay, that's sort of the idea. Again, this part is not super. It's not the biggest deal if you don't fully understand this computation. All I really want to point out though is that there's some sort of way to go from these expectations back and forth to some kind of Hilbert I guess Hilbert space product here. KW. So there's some kind of way to go back and forth between these correlation functions and these Hilbert space values. Okay. Okay. I think I might have
The point is that there's one process that's happening and it's being evaluated at time 0 and time t. But this expression, A1 of x0, A2 of xt, you're just drawing from, there's a probability distribution for all the paths. And you're saying for each path, evaluated at 0 and at t, evaluate this, and then, sum over all of those things. But you need to sum over the paths, right? You need to let the process happen and then sample from a single instance, x0 and xt, and then you integrate over all paths.
All right, thank you, Marco. That's that's a very good explanation of this. Yeah, I want to go back to a more specific example, and hopefully that'll clarify some of these matters. Okay. So I'll give you an example of a concrete Euclidean quantum mechanics system. So example. This is going to be the Ornstein-Uhlenbeck process. So it's going to be some process again, xt, where t is going to be an r. Okay, so it'll be kind of just something like this, some random curve here. Okay, and it's going to be so xt is going to be a centered Gaussian with normal 0. And this and mean either minus alpha absolute value t over 2 alpha. Okay. So at every time, it's going to be a center normal value, and it's going to have a particular variance. Now, if I look at this, the expected value of xt, xs. Okay. So knowing this would tell me the distribution of it. So this will give me, this is going to equal e to the minus alpha, t minus s over 2 alpha as well. Okay. So I have, yeah, alpha is positive. So this is just some distribution. And from here, I can also say that the xt, if I look at the law,
it's peaking as time goes forward, it's getting more concentrated. I don't understand.
Oh, this is a good point. Okay, sorry, I think there might be a 1. Is there a 1 minus here? 1 minus, sorry, there's a slight error. Okay, I can check my notes in a second, but the real properties you need are expectation of xt are going to equal 0, and it has this following correlation structure. I don't remember exactly the distribution every fixed time, but the key point is that the distribution will not depend on t at all. So what I wrote originally was incorrect, but these 2 points, if you trust me, this defines the distribution fully. Okay. Now from here, I can also look at the law of xt, given x naught is equal to some little x. Okay. So if I know at time 0, I'm at x. Okay. What is my law at time t? Okay. So what does this look like over here? And this is given by the following. So this is given by e to the minus alpha t times x plus the normal distribution of 0. And I think this is 1 minus e to the 2 alpha minus 2 alpha t over 2 alpha. Okay. So roughly what this says is for a very, very, very large t, this will go to 0. Okay, so this is a law. Okay, and then from here I can look at kf at x. Okay, so if I look at this is given by expected value f of, and it's going to be kt of f evaluated at x. This is the expected value of f at xt, given that x at time 0 is given by little x. Okay. And then x at time t, given x naught of little x. So this is the key factor I want to use. So I'll plug this in here. This is equal to the expected value of f evaluated at this Gaussian distribution here. So it's going to have a mean e to the minus alpha t little x plus normal of 0, 1 minus e to the minus 2 alpha t over 2 alpha. Okay. And then this is a Gaussian distribution. I know what the distribution function for a Gaussian is. So this is given by some kind of very explicit integral, f of x d mu of x, where mu is exactly the law of this Gaussian over here. Okay? Any questions? Okay. I'll slowly erase this board. If you have any questions, please speak up. Yeah.
What does this, when you define the law?
Yeah.
Right, are you just
I'm saying with the distribution.
projecting what you erased
Yeah.
Tell us what-
Yeah. So what I wrote originally was incorrect. I could check if you really care, but yeah.
I'm just trying to understand what this probabilistic process
Yeah.
is doing. Is it like some kind of random motion of a particle on a line?
Yeah,
Is it
yeah.
connected to zero? I just need to know.
Yes. Actually, that's a very good way of explaining it. Thank you. So this is kind of like a mean reversing process. It's kind of a random process, a random particle doing some kind of walk. It kind of wants to go all the way back to zero always, so it'll always center itself around zero. Okay.
And it's getting pushed stronger to zero as time goes on. You
Um,
said it's e to the minus alpha t x. So it's squashing it down as time goes forward.
this is a good question. I should check this. The distribution should be invariant. So let me check this quickly. So this is going to 1. Sorry, just normal 0, 1. So it's for a very large t, it looks like a normal distribution with mean 0 and variance 1, right? So this is 1.
If you're starting at point x,
Yeah.
then where are you ending up?
So this goes to 0, right? This goes to 1, right? 1, I guess 1 over 2 alpha. Right? Okay, so if let's say I know it myself at time x, or this is a time t, I know I'm x, okay? I run it for a super long time. Well, I've forgotten about this entirely. This is 0. And I'm just a centered Gaussian distribution with
Pulls it
variance.
in with some noise.
Yeah.
Yeah. Okay.
Yeah. Okay. So this is process that's pretty easy to define overall. And this kernel k, okay. I know how to evaluate k explicitly on a function. So I'll pick particular functions I like now. Okay, so if I look at these functions here, e lambda, all right, hat of x, this is going to be exp of I lambda x times exp of lambda squared over 2 alpha. The 2 might be off, but it's something roughly like this. So this function here, I'm going to want to use this later. And this is related to the Hermite polynomials because this will be the generator of all the Hermite polynomials. So I've looked at the sum for all n from 0 to infinity of I lambda power of n over n factorial hn of x. So these are going to be Hermite polynomials. Okay, this equality is going to be true. Now, this is some explicit function, and I know how to take k and evaluate on a explicit function. So let me do that. It's a pretty straightforward calculation, but I don't want to go through all the details. So if you want, you can believe me that if you go through this process and you integrate, you're going to get back e lambda e to the minus alpha t evaluated at x. So basically kt, all it does is it takes this parameter lambda and it changes it. It multiplies it by e to the minus alpha t. Okay. But let me plug in the series, okay? And I'll bring the kt inside. So this implies the sum from n bigger than or equal to 0 of I lambda to the n over n factorial kt acting on my Hermite polynomial hn. Well, this is equal to n bigger than or equal to 0. So it's going to be the same thing, but with a e to the minus alpha t. I can bring the alpha t outside of the n. So this will be I lambda to the n over n factorial e to the minus alpha nt hn. Okay. So in particular, this tells me that kt applied on hn is equal to e to the minus alpha nt hn. Right? And then now here I'm going to Wick rotate. So let u of t equals to k of, I think I want to do minus it, but it doesn't really matter so much. Okay, u of t equals k minus it. So the way I can analytically extend it is just say, well, the Hermite polynomials later on my Hilbert space will be a basis. So I can define this operator u by what it does to these hns. And by this relation here, all I need is I need u of t applied to hn will equal the same thing here by plugging minus it. So e to the I alpha n t hn here. So it's going to be, this is sort of going to be my Wick rotated time evolution operator u of t, okay? And now let's look at what it's doing. It's taking these Hermite polynomials, and it's all it's doing is multiplying by some kind of phase, e to the minus I alpha nt, which is basically an n-dependent quantity. Larger n, the bigger the phase change, okay? But there's actually a quantum mechanical system that does exactly this. It takes Hermite polynomials and it time evolves them and multiply them by a phase that's independent, okay? This in particular, so this here, u of t is the time evolution operator for the simple harmonic oscillator. Okay, so I haven't picked my Hilbert space. My Hilbert space would just be like L2 of R with like whatever measure you want, mu of dx. Okay, and I'll have this this time evolution operator. Okay, so I've started with this Ornstein-Uhlenbeck process. It's just some random process on R. I look at this K, I Wick rotated it, and I've ended up with a simple harmonic oscillator. Okay, so really the identification you should think is OU.
Yeah, sorry, isn't there a problem, like, shouldn't it be Hermite polynomial times a Gaussian or something?
Yes, this is the Gaussian.
Okay, but in terms of the stationary states, it shouldn't be just the HMs.
So for these series to be exactly equal for all t, the only way these can all be equal is for these terms to always be equal, right? Because this can be true for all lambda as well. This is true for all lambda.
I'm just saying that
Yeah.
the stationary states for the constant harmonic oscillator are not polynomials. The polynomials times, yes.
Yes, but these HNs, it's a good question.
Is the Gaussian in the measure?
Yes, sorry, yes. The Gaussian in this formulation, I've thrown a Gaussian in the measure. So actually now the stationary states are exactly Hermite polynomials. So you're used to having the Gaussian term be multiplied with HNs, and that's going to take the measure to be just dx. But if I put the Gaussian in the measure, then it's the stationary states are just exactly Hermite polynomials. Thank you for the save there. Okay, OU process xt. I go back and forth between this and a simple harmonic oscillator. Okay, so hopefully this example is a little bit more clear. But okay, so in this example, everything worked out. Okay, yeah.
So you just through the study of this problem, you knew what functions were. So you just introduce an example.
Yeah.
The f from this previous word. Here
Yeah,
you were saying what kt it does.
Yeah.
So can you just restate the last outcome of this board? So you're saying if you want to compute kt f of x,
Yeah.
it becomes an L2 it becomes a Hilbert space in a
Oh, it just
what?
I just-
Still understand.
so this here is some exactly a Gaussian, right? So it has some distribution. So this is some random variable. I guess maybe I'll circle this thing here. Sorry, a little bit of, so this is like y. Let's say y is some normal distribution with mean e to the minus alpha t x and norm. I don't know the space, but you can read over here. Okay, so I know that the probability that y equals little y. So I know that the distribution of this is given by like 1 over root 2 pi times the standard deviation for normal and e to the minus y squared over 2 sigma, right? So this is just the distribution function for a norm. And so in particular, this to get this expectation, I just need to integrate e f of x, where x is drawn by this measure here. So really it's just integral of f of x times this quantity here plugged in. So p of y equals to x and then dx. Okay, so it's a very explicit integral.
Where's the x dependence? I mean, it looks like you're integrating x out.
Maybe I'll call this y here, if little y if you want. But so again, all I have is I have a Gaussian here. I'm taking expected value of e of f, a value at a Gaussian distribution that I know very explicitly.
Right, but what you end up with should depend on x. It should not be a number.
Yes, it'll depend on x. Yes, yes. So this would be a dy. You're completely right. Yes, because it's so this will be y minus the mean squared, y minus mu squared, and then mu will depend on x, little x here, because x affects the mean. Yes, yes, yes. No, these are very good questions. Thank you for the. Any more questions? I want to make sure these parts are clear. We good so far? Okay, okay. Anyway, it seems kind of miraculous, right? That I took a process xt. Now I can always define kt in the way I did, be it this kind of semi-group, expected value, etc. But from there, the fact that when I Wick rotated, I got a quantum mechanical system, that's a little bit of a miracle. That's a little bit of a miracle. If you do this for any like random process, if you do this for any process, most likely you won't get back a quantum mechanical system, okay? So to ensure that when you do this Wick rotation, that you get a quantum mechanical system, we'll need to enforce some restrictions on the distribution of xt, okay? So, okay, so how do we know that like xt and then you Wick rotate to some Hilbert space H with some operator time evolution operator U? How do you know that this works, right? And there's going to be a few restrictions on x. Okay, so need 3 restrictions on the law of x. Okay, so this is like a baby version of a much stronger theorem. So this is going to be Oster, Walder, and Schroeder. I'll write a stronger version of the theorem later. I don't know the exact date, but it'll be sometime in the 70s. It's pretty old, but okay. So I'll say this this Wick rotation, it works, okay? Meaning that this process here gets me back Hilbert space in a unitary one parameter family. If a few things. So one is I'm going to want xt. I want xt to be stationary in law. Okay. Meaning that for any xt, I want this to equal in distribution to xt plus s. Okay. Why does this come in? Well, it's because when we started off on the Hilbert space side of things, our ground state was not affected by time evolution, right? So evolving my ground state by u of t did give me back my ground state, okay? And because this ground state was invariant in respect to time, when you push everything forward, this corresponds to asking that your distribution does not depend on time as well, okay? This is the first property. The second property is going to be.
Can I ask a question about
yeah.
that?
Yes.
What you just erased, you had that the law, it was like law of xt conditional and x0 is equal to x is something that depends on t. Is that because you're conditioning at time 0?
Yeah, so I'm conditioning at time 0, and I'm asking what the process looks like at time t later, right? So 0 and t are things that are fixed.
I
But
see.
all that really matters is the difference between t and 0 is, well, t. So I could have done s and s plus t. So it's stationary, so it doesn't actually matter so much.
Okay, thanks.
What was aspect of the previous example that was independent of t?
Oh, yeah, so in that previous example, I wrote law of x t given by x naught equals x to equal like either minus alpha t x, right? So yeah, plus the normal, right? Well, really, I could have changed it. I could have put in an s over here and a t plus s over here, and this right-hand side would never have changed. So that's what I mean by stationary in that example. Okay. All right, any more questions? Oh, yeah, sorry, this is a bit of weaker condition. Yeah, so what I mean is x, yeah, what Jeremy means here is xt at any given particular time t is given by some normal with some standard deviation, let's say sigma, I forget what it is exactly, but it's the sigma is not t dependent.
1 minus e to the minus 2 alpha t.
Oh, that was only at this conditional law
Oh,
level.
I see.
Yes. In fact, I think this might just be 1/2 alpha. Yes, it was 1/2 alpha. But okay. So that's in the Ornstein-Uhlenbeck process, it was stationary in this sense. Okay. The law at time t was always the same, no matter what. Yeah. In fact, the statement's a little bit stronger. I could almost said at time the law of xt1, xt2, xtn is also the same as the law of xt1 plus s all the way to xtn plus s. This is more precisely what I mean, but I don't want to be too precise right now. Okay, so I'll erase this. So the first property, hopefully we're okay with. The second property is going to be a little bit uninteresting. This is just going to be some kind of regularity assumptions. On the moments of xt. So meaning that if I look at the expected value of the integral of xt against some function ft, and I look at some power of it, I don't know if it's square or something, this is less than or equal to something that depends on f, okay? The statement is not super important. I won't go back to this point at all. This is so you can analytically rotate and analytically extend and rotate your Schwinger to your Whiteman functions, okay? So this probably is not so interesting, but there is another third property, which is very restrictive actually, and this is reflection positivity. So I need to spend a little bit of time explaining what this is, because this is actually a very important property. So I'll go to this board here, okay? So really this reflection positivity, it comes from the fact that we want our correlation functions to come from some kind of Hilbert space as well. But Hilbert space has some like positivity, right? Like if you take the inner product of something with itself, well, that's norm. And so you get something that's positive, right? So it's really this property, this positivity of your Hilbert space inner product that is being instantiated as reflection positivity on the Euclidean side. So let me be a bit more precise. Okay, so let's say I have some kind of operator f on my Hilbert space. Okay, I'm going to define what is called theta f of x. Okay, so this operator is going to act on the entire process potentially, so t and L and R. It acts on the entire process in this way. So maybe I'll write x sub t. All it does is it takes f and evaluates it at the flipped version of this process.
Are you still in the situation where H is like L2 on the?
Yeah.
Okay.
Yeah, I guess in Euclidean quantum mechanics, it'll basically always be L2 of R. Okay, this won't be the case when we go to quantum field theory, but for
But
now,
you're also specifying what the measure is on R? Or
in principle, I should.
But that depends on the XT.
Yeah, yeah,
Okay.
it will.
fine.
Yeah, yeah. Okay, so all this does is this takes the function x of minus t, okay? And it flips it at t. So this is the flipped version of your process now. That's okay. So now this is sort of a definition here. And reflection positivity is a precise statement. It says that if I look at expectations like this, okay, so if I look at theta f at x, this is about the entire process. I look at the complex conjugate, and I look at this product here, and I look at this inner product. So sorry, look at this product and take an expected value. I need these quantities to be positive. Okay? So I guess where does this come from? Roughly comes from the Hilbert space positivity. So let's say I looked at my Schwinger functions, which are okay. If I start with the process of xt, the Schwinger functions are the correlation functions that I wrote earlier, but I also want them to be Hilbert space inner products for a particular Hilbert space. So if I look at this quantity, a value at, let's say, T1. Thank you. I guess maybe S is a better letter though. It does start with an S, right? I don't know. Anyway, this is 50 years old. I can't change it anymore. Anyway, okay. So look at A2, A1, A1, A2. Second. Okay, I'm missing one T. Okay. This input I wrote it slightly wrong, but I'll fix it in a second. Okay, so I want this to be given by some kind of inner product here. So W, and I want this to be A2 K of T1, A1, let's see, A1 K of T1. 1 second. I think I always mess up the T's here. So let me see exactly what I want to write. Let's see, 1 second. Okay, so let's say I want something like this. So this is going to be A2. So A2 K of T1, A1, and then A1 K of T1, A2, and my state W, okay? And this corresponds to the Schwinger function where I did T1 kind of twice, and maybe there's like a 0 in the middle actually. So T1, 0, T1, there we go. And now, so there's 3 kind of time increments, and there's 4 operators, A2, A1, A1, A2, okay? Okay, so if I write this, and if it happens to correspond to some Hilbert space inner product, I get something like this, okay? Now, when I conjugate these A2s by these Ks, I'll get back a self-adjoint operator. So maybe there's a bit of calculations that I'm going to skip here. But this corresponds, so I can kind of move this to the other side. So this will be W1, A2, K of T1, A1, and then the same thing here. A1, K of T1, A2, W here. So this is going to be some kind of norm, which are going to need to be positive, okay? So when this is defined just in terms of these expected values, so this would be my process, I guess, A2 evaluated at X at time 0, A1 evaluated at X at time T1, A1 evaluated at X at time T1, A2 evaluated at X at time T1 to T1. Okay, so the definition in terms of the process is given by some correlation function, which I think I wrote correctly, but I possibly messed up. But this correlation function, I have no reason initially to think it's positive. But if I did come from a Hilbert space, that means this correlation function has to have come from this Hilbert space inner product, which has to be positive, okay? And then this quantity here, this corresponds to expected value of this theta f of x, f of x, where my theta, or my f, sorry, corresponds to evaluating this at f of x going to equal a2 of x sub minus t1, a1 times x at 0. Okay.
Very German way of giving talks. It's like a long sentence that you only understand what you're doing at the end. See, like, I
Yeah.
would like to know that F is what? What is that?
So
A1 at 0, okay.
yeah.
Now I can kind of.
And there's also, I'm also using stationarity here, so I'll throw it times 0, but actually I'm sort of time minus t1. But it's all stationary, so I can move everything back, right? So this is minus t1, this is 0, this is 0, and this is t1, right? This is the exact same thing as I wrote a second ago. But now this is equal to this with this particular f.
Okay, wait. So let's go back to this reflection positivity.
Yeah.
So what is that?
F is going to be some operator on my Hilbert space.
What kind of?
In this example, okay, I guess in this example,
Self-adjoint, skew-adjoint, what?
self-adjoint.
Self-adjoint.
Yes.
Okay. And theta is just doing this
Time reversal. Yeah.
So what does the bar mean?
Complex conjugate. So
Conjugate of what?
in principle, this can be complex numbers actually. This is like a complex Hilbert space. So this quantity here, when you do this, this is a this is potentially might be the same as like doing an integral of this quantity with a bar over here, for example, and this product, for example. So this is where the complex conjugate comes from. It's not too important.
So you're just giving an example
Yeah.
of why this.
Yes.
Why this
Yes.
function is the way it is.
Yes. But really all it's coming from is the fact that if you want these correlation functions to also at times to also be given by these Hilbert space inner products, certain correlation functions are going to be forced to be positive because of the norms.
But you haven't yet written what this condition implies about the process.
Yeah. I'm gonna say that in a second. Yeah. So this is a very restrictive process. So I guess I'll mostly just say it verbally. But when a process is just an R, okay, when I'm just on xt, okay, when it's just a process on R, this condition, I'm not going to give the proof, but it's relatively short. It forces my process to either be Ornstein-Uhlenbeck, a convex linear combination of Ornstein-Uhlenbecks, or a limit of convex linear combinations of Ornstein-Uhlenbecks. So essentially, on dimensions 1, this is kind of trivial. Everything's going to be basic Ornstein-Uhlenbeck. Okay, it's a very restrictive condition in this case. But more generally, okay, so
But wait 1 second.
Yeah,
So
yeah.
in this theorem,
Yeah.
right, it is phrased this way. It's not expressed in terms of the process. The result, like the condition of reflection
Yeah.
positivity is not expressed as a condition on the process.
So this is a statement on the law of the process, right? So this is saying if like any operator f evaluated at x, do this kind of theta bar and then multiply by f of x, and I integrate with respect to the law of x, right? So
You express it this way, then aren't you kind of assuming what the Hilbert space actually is and that the process is happening in R? Like, so you're expressing it. with an assumption on what the Hilbert space
I haven't constructed a Hilbert space yet. At this point, there's no Hilbert space, but the hope is that there will be a Hilbert space at some point, right? So let's say this is going to be the actual definition right here, and this is going to be the hope, right? The hope is that this is also true for some Hilbert space. I don't know what the Hilbert space is, but I want to hope that it is there, right? If I have any shot of hoping that is there, then certain quantities are going to have to be positive. But the Hilbert space is not there yet. All I know is that I have some random process on R, and I have some operators act on this process. Yes.
So your Hilbert space will depend on the process X. Your function X,
Yeah.
which you have to set the condition for, will depend on this Hilbert space.
The function f shouldn't depend on the function f will have to be self-adjoint. So yes, it will depend on the stationary. Yeah.
You need to construct the Hilbert space to get those functions that we can use to set the expectation.
Mhm.
But you don't know if you are going to get one space.
These are good points. This condition, so maybe perhaps a little bit stronger. So I'm going to ask that this is not true for self. I'm gonna ask for this is true for all cylinder functions f. So this is a little bit stronger condition, okay? I'm not gonna assume anything on f except that it might be a cylinder function in the sense that f only depends on the process x at finally many times. But that's all I'm gonna ask. So this is gonna true. I should say this. This is true for all cylinder functions f. Yeah. Oh, it just means it depends on f of x. It's going to equal f at like x of t1 for x of tn for some choice of t1 tn. But any particular f only depends on x at finally many times. That's all I'm saying. Yeah. But okay, so given these, yeah.
Is the random walk on R such a process?
So
Or is it, because you said that it's only OU and it's.
yeah, so a random walk on R is not going to be reflection positive, for example. So it won't be Euclidean it won't be a Euclidean quantum mechanical system. Basically, the only thing that you can do in this dimension is Ornstein-Uhlenbeck, or combinations of that. So in this dimension, it's not super interesting yet. Okay, yeah. I mean, I can still take limits of Ornstein-Uhlenbeck, so it's still there's still a lot I can do. Like it's not just Ornstein-Uhlenbeck, but everything's gonna be a limit of that. Okay. All right. Are we okay if I erase this board? Okay. Good. Also, I'm like probably like 3/4 done. If you want to take a break, like, do people want to take a break or do you want to continue?
Sure.
I'm okay continuing. Okay. Okay. Perfect. If and again, please keep asking questions, guys. I don't want to like lose everyone. Definitely giving a probability talk is very interesting, and I don't want to assume any probability, but it's good. It's good. With your questions, I think we're getting through it. Okay. Now let's say, given some like Euclidean quantum mechanical system, let's say mu, which is like the law of some xt, let's say. Okay. Can I get more Euclidean? Like, can I change things in such a way to generate another one? Okay. And you got to change things in a careful way because you don't want to like kill reflection positivity. You also need to keep stationarity. The regularity condition isn't too important. That's pretty easy to keep. Yeah.
Like an EQMs.
Oh, yeah. So it's a thing that's going to satisfy the 3 conditions. So, thank you. EQM is given by the law of xt, where xt is stationary, reflection positive, and has the regularity conditions.
So I need you to help me get over this hang up that I have, which is why are you always assuming that you're on R? Is it just for
Oh
simplicity?
yeah, right? There's no like,
I see.
yeah.
Thinking
It-
related to the fact that it's one-dimensional.
Exactly. So in quantum mechanics, you only have a time dimension. There's no space dimensions. When you rotate, you're gonna have exactly one space dimension, and there's nothing else, right? We're in a very simple world here, okay? We're just in quantum mechanics. In quantum field theory, we'll have more things going on, okay? But for now, it's gonna be pretty simple. But I want to do all the hard thinking in the quantum mechanical world. That's okay. Okay, so the one thing I can do. So here's a trick. Is I can do what's called a Gibbsian perturbation.
Can I ask a question? You
Yes,
said
yes.
you just said that there's basically only this Ornstein-Uhlenbeck. Those are the only EQMs.
Limits of that. Everything's gonna be generated by. So either I'm Ornstein-Uhlenbeck, I'll be a convex linear combination of independent Ornstein-Uhlenbecks, or I'll be some kind of limit of that.
So right now, what you're describing is how to get one of those limits or one of the convex combinations.
Yeah. So something a little bit different. Yeah, something a little bit different. It'll be like another kind of Ornstein-Uhlenbeck like object. Okay. But when I go to higher dimensions of quantum field theory, it won't be something as trivial of a change. Okay. It'll be more substantial. Okay. Anyway, given some potential b. So let's say I have some function b from r to, I don't want these to be positive. You don't have to make it positive, but I want it to be positive. Okay, so I have a Euclidean quantum mechanical system, mu. I'm gonna construct a new one. I'll do mu sub t, and this is gonna be the law of this evaluated at some xt. Okay, so at some path. It's gonna be given by mu, but with some radon-Nikodym derivative. So I'll write one thing first, and I'll explain more precisely what I mean. But for those of you that do probability, you probably will understand this immediately. So exp of minus integral of minus t v x of t dt, and then this is mu of xt. Okay, so but this is going to be my old measure, mu of xt, and then some radon-Nikodym derivative in front. Okay, so more precisely, if I look at an expected value under this nu t of some function f at my process, okay, it's going to be the same as doing the same thing but multiplying by this function in front. So zt inverse, doing the expectation over mu f of xt, and then exp minus integral minus t v of xt dt, and then yeah, this is a mu integral, and these z just guarantee that I'm a probability measure. Okay, just a normalization to be a probability measure. Okay, so if I do things in this way, the proof is very short, but I'll skip it for time. But because this is symmetric, when I flip time, this distribution here is symmetric. It's still symmetric when I flip time around 0. Okay, so this guy is still reflection. So nu t is still reflection positive. Okay, so it's still, because it still has this invariance around 0. It's not stationary anymore though, because I'm on a finite interval minus t and t. So if I translate, I don't get back the same interval. So I need to take t to infinity. Okay, so this is reflection positive, but not stationary. But if I can show this limit exists, if nu, which is equal to this limit as t goes to infinity of nu of t, if this exists, then I have a new Euclidean quantum mechanical system. Okay. Yeah. All right. So this is a quick kind of just sort of natural thing you would do to create a new kind of perturbation of your original theory. Okay. So now we'll do some quantum field theory. Okay. And I'll be a little bit brief on the quantum field theory side of things, because when you go to Euclidean space, it's not going to be actually a huge difference. But okay.
But normally, so this E sub mu, that's the original measure.
Yeah.
of perturbation.
Yeah.
So normally they make the distinction of the free theory and the interactions.
Yes. So V would be the interaction.
So, but is it necessary to interpret it that way? Like the original thing, does it have to be free in some sense, or is it just that you have something and you're adding something to it? It's not necessarily a free theory that you're adding an interaction term to.
So I'm not entirely sure. I don't really know my quantum field theory super well, but the jargon is that they describe typically these mu's will be like either ordinary process or like a higher dimensional analog. We call those free theories. Part of the reason that they call it free is because when you do Wick transform back, you get a free Klein-Gordon quantum field theory. I don't know what that is, but apparently it's free bosonic quantum field theory. But in that sense, they call it free, and then the V they say is the interacting potential. But again, I only know the jargon.
In the expression for the new expectation, you have like E sub mu of f of x sub capital T.
This should be this should just be the same thing, right? Is that better?
Yeah.
Okay, cool. Yeah, sorry. I write a lot of stuff randomly sometimes. Okay, any more? I saw a hand here. Yeah.
Like take the exact same thing, but take a W, and then everywhere you put this new limit thing, and I get a new measure.
Sorry, put a W. What did I put a W?
Oh, so I'm saying I had a new function, W. You started with this
Yeah,
perturbation.
yeah.
So the output of this process was some new measure.
Yeah.
New. Could I redo the whole thing?
Yeah.
Where new is new?
Yeah. All I do is I started with some Euclidean quantum mechanical system. I do this perturbation, and things typically work out. I'll say there's some small technical things. So, okay, I won't say anymore. But yeah, this basically works. Believe me in my word, and I'll give you a better reference later. Okay. Okay. I'll do a short little part on quantum field theory to Euclidean quantum field theory. And I'll be pretty brief on this quantum field theory side because I want to get to this EQFT quickly. But okay, so originally, we had some kind of Hilbert space, and I'll still have some kind of Hilbert space, but this will be some H is some Hilbert space, and it'll be some maybe L2 space over Minkowski space. So it'll be kind of, I'll be very, very, very vague here, but kind of lying over Minkowski space. M n plus 1. So it'll be maybe some kind of function space over Minkowski space here, okay? And then before, the key thing I had was I had this unitary time evolution operator, okay? Because in quantum mechanics, the only thing I could do is move time forward, right? But now, if you imagine, I'm actually on a field now. So this is Minkowski. There's maybe 3 dimensions here, or 3, and then this is time. Okay, so now when you have space and time, there are different things you can do to your fields, right? So you can translate I guess my states are still going to be, I guess, Hilbert space of states, I guess. So my states are still going to be fields, and there are different things I can do to the fields, right? I can still time evolve it, of course, but I can translate it, I can rotate it, and I get a Lorentz boost, right? So those combination of things is the Poincare group, right? So in particular, I have what I have is if P is the Poincare group, okay, and I have what is pi, which is I guess a unitary representation of P, okay, so meaning that pi of P, this is going to be some bounded operator on my Hilbert space, okay? Okay. Now, I still want a ground state, okay? I still want a ground state to make all this stuff work. So before, I just needed my ground state to be invariant with respect to my unitary time evolution. Here, it's going to be the same thing. I'm just going to make it unitary. I'm going to make it so that it's not affected by these Poincare transforms, okay? So let W be a ground state if, let's say, pi of P acting on W, again, this gives me W, okay? So again, the same kind of analog as before. Before I said U of T, but now I just have a bigger group, right? So to go from 1 dimension, I think this is a 10-dimensional group, but otherwise everything's the same, okay? So I'm gonna again assume, so again, always I'm gonna assumption. I'll assume that there exists I guess people also call this vacuum state as well, but I'll call it ground/vacuum state. Which is cyclic. Again, meaning that I can get to any other state by hitting it with other operators, okay? So now once I have this assumption again, then I can define my, what do I call it? Whiteman functions. I can define my Whiteman functions. Okay. So before, okay, I'll write the wrong thing first and then I'll fix it in a second, okay? Before I had T1 to Tn-1 and operators A1 to An, okay? And this is equal to my Hilbert space inner product, okay? So that's what I had before. Only real difference now is, well, instead of T's, maybe I'll have n-1 elements of the Poincare group, right? So it's a bit of a bigger function in the sense that the input is bigger. But if I know my functions, I know everything again, okay? So key is that the Hilbert space is, I guess, captured, I'll say it loosely, by my Whiteman functions. Okay. Okay. And I'm going to do the same kind of operation, but I'm going to take my t and I'm going to just go to imaginary time and see what I get. And I'll get a Euclidean quantum field theory, and things are going to feel pretty similar to how they did before. Let me just check the time. I don't want to kill too much. I should be done in 15 minutes. Hopefully that's not too bad for you guys. Okay. Okay. So in this case, so I have my QFT, which is like my Hilbert space lying over my Minkowski space. There's n plus m n plus 1. And I have some kind of metric on Minkowski space minus dt squared plus dx1 squared plus dxn squared. Right? And now we go from Hilbert space to, so t goes to it. Again, this is my Wick rotation. So not too many more things are going to change. So one is mn plus 1. This is going to go, so before my ida operators, Hilbert space over mn plus 1. Now I'll get some kind of Hilbert space or some kind of space of maybe continuous functions over Rn plus 1. That's what you might expect maybe initially. So before I had a C of R. Now, for regularity reasons, you actually will never get a function. So you'll get a tempered distribution. So this is tempered distributions over Rn plus 1. So these are just guys that eat Shor's functions, okay? But this is not like a crazy distinction. It's just the unlucky regularity reason, okay? But this is the nice part, okay? So the reason why, so when you do t to it, this metric here becomes d, so if I guess x naught equals it, this is just dx naught squared plus dx1 squared plus dxn squared, okay? So this metric here, once you do the Wick rotation, you're just a normal Euclidean space, okay? So when you ask, so this is going to be some process x ff, or for Shor's functions f, okay? So this is going to be an element of this space. Yeah.
What term are you using for the S?
Schwartz, the Schwartz?
Oh, the Schwartz.
Schwartz function, right? Okay. That was a German word, right? My German's not very good. Okay, but okay, really not too much has changed, and the conditions I need are going to be pretty similar overall. Okay, so I'm going to ask the kind of the same question.
Sorry,
Yeah.
what kind of processes are these now?
So before we just x evaluated at time t.
Yeah.
Now you might think maybe x evaluated at some point little x in Rn is what you'd want. Regularity reasons means you'll never get that.
So you can't.
You can't evaluate the points. You only evaluate the functions.
Okay.
You know, functions are also always distributions as well, of course. Like if I had like, maybe like this is a small aside, right? Of course, some just basic analysis. If you just have a function f in like c of Rn plus 1, well, f acts on another function g in this kind of way here. F integral fg. Maybe if I'm like in some L2 space, but you know, functions act in the same way as distributions sometimes, but not all distributions are functions, of course. But okay, this distinction is more technical, but I want to ask the same question, okay? Let's say I gave you a random tempered distribution, and I ask whether or not it came from a quantum field theory. I asked whether I could do this Wick rotation backwards, okay? So almost all of the explanations are going to be the same. In fact, they will be exactly the same. So
Over there, F is an element of S of R what?
n plus 1. Yes, right?
But you're telling me that the process itself is an S prime Rn plus 1?
Yeah, this is what it means to act on. This is what it means to be tempered distribution. Is you can think of it as being a Gaussian or some kind of process indexed by Shor's functions, right? So at every Shor's function, you give me a number. That's what that means. So this is a funny way of running a temperate distribution.
But it's a probability distribution on the tempered distributions?
Yes. It's a probability distribution over temperate distributions. Yep.
A measure on the space of distributions.
Yeah, it's a probability measure of the space of distributions. Yep. So your Euclidean quantum field theories will always be this. There'll be these probability distributions over these spaces. So I guess I'll write as a definition actually. So actually no, I'll write theorem first. Okay. Okay. So I'll be. This is going to be the same version but more real version of it. Osterwalder Schroeder. Okay. So given random, I guess x of f or fn Schwartz or n plus 1. Okay. I guess you can, again, I'm writing very informal, but hopefully that's fine. Quick rotate to a normal, quantum field theory if the following is true. Okay, so so before we just had, so here I'm going to need full Euclidean invariance, okay? Right? This means that the law of x is completely unchanged if I do any Euclidean transform of Rn plus 1. So if I translate in any direction or if I rotate in any direction, okay? So maybe I'll have a quick aside. Before, it was just stationarity, right? So this is back in Euclidean quantum mechanics. And that's because I only have one operation, right? So that which is just move forward in time. And that means I need to be stationary. Now there's way more things I can do. So, but again, I want my ground state to be stationary with respect to all these things. So that means I needed to be completely invariant. I need the measure to be invariant under all the Euclidean transformations. So this is the only real difference. Everything else is going to be the same. Reflection positivity. Now we're in higher dimensions, but it's kind of the same thing. You pick any hyperplane, you flip it, and then the same kind of map is true. So expected value, theta. I probably need to give you a hyperplane, so that's given by like a normal f x, f of x. This is bigger than equal to 0. Okay, so it's basically the same condition. Yeah.
Point one, like before you had xt, so it made sense x of t should be xt plus s.
Yeah.
Now it's x of f.
Yeah. So what I'm yeah. So let's say O is in the
on those functions by transport.
Yeah.
Okay.
Yeah, this is a key point. I should just clarify this, but if O is in the orthogonal group, S O R n plus 1, that's how you write it, right? Okay, then O x of f is equal to x f of O. I'll put it on the inside. X, I guess x O f, which is just x f O with like a dot here. Okay. Oh, yeah. Well, hopefully the idea of all you're doing is like doing an orthogonal transformation on the underlying space is clear. Yeah. Okay. And then this is a regularity conditions. Not too interesting. Okay. And then if you can do all these things, you can get back quantum field theory. You can construct a Hilbert space in a very specific way. And then the definition of a Euclidean quantum field theory is a random process x f in Schwartz that satisfies 1, 2, and 3. Okay. Okay. So then the last 5 to 10 minutes, I'll give you the canonical example. I'll do the Gibbsian perturbation of it to give you the easiest non-trivial example, and then I'll tell you why this field is so hard. Okay. Also, I'll tell you the new things that probabilists have been doing for the last 10 years.
Yes, plastic, PDEs.
Oh, that will come in the very end. The new techniques are the stochastic PDs. So, which I'm not going to define, of course. Okay, so the example, this is going to be the Gaussian free field with mass m. So an m just going to be some fixed parameter bigger than 0. Okay, so if I look at x, evaluate any f, so this is going to be some x, right? So if I take x, evaluate at f, it's going to be this is going to be some normal distribution. It's a mean 0 and variance. I forgot, but it's not too important. Okay, but the key thing is you want to say what the correlations functions are. So you write x of f, x of g. So f and g are just two Schwarz functions. And I'm going to tell you this is giving my default integral. I'm going to take a Fourier transform of f hat bar of k, and then g hat of k, and to do k squared plus m squared, and I integrate over dk. Okay, and this is an integral over Rn plus 1. Okay, so I define it via the Fourier transforms here. And I believe this is the same thing as doing this operation, Laplacian minus m squared inverse, and then g and then f. But don't worry what this means. Okay, this is how you would make sense of this map here. Okay, but okay, so I've given you a Gaussian process. This defines it pretty well. Okay, now this, because of the structure of this correlation function, maybe you can believe me that this is kind of, when I rotate it or translate it, everything here is fine. You know, when you translate things that correspond to just adding a phase to your Fourier transforms. Okay, I don't want to give a proof, but maybe fact is x is RP. It is Euclidean invariant, and in particular, it is a Euclidean quantum field theory. And in fact, if you take x and you rotate backwards, so this is Wick rotate. I Googled this earlier today. You get back a, so the Klein-Gordon quantum field theory with mass m bigger than 0, which is supposed to be like a free bosonic. I don't know what any of these words mean, guys, but maybe you do. I don't know. Have you guys seen this before? Okay, so this is what this corresponds to. Okay, but now given x, I want to change it now to get something new. Okay, so this is going to be my canonical example. This is like my higher dimensional analog of Ornstein-Uhlenbeck. And actually, in fact, I can construct x with Ornstein-Uhlenbecks. If we want to do this, maybe I'll say it quickly, is you can take a L2 basis for your Fourier transform space, because like a Fourier basis. You multiply each Fourier coefficient by an independent Ornstein-Uhlenbeck, and then you scale things in the right way, and you'll get back a Gaussian free field, roughly. So this is built off of infinitely many Ornstein-Uhlenbeck processes. Okay. Let's see. So I want to do the Gibbsian perturbation kind of in the same way I did earlier. Okay. Things that are going to break, but that's fine. It's what happens in math, right? So Gibbsian perturbation. Okay. So let's say mu is like the law of my Gaussian free field F. Okay. So I want to find a new law, nu t of like evaluated at some temporal distribution x, to be given by, well, there'll be some normalization again. And then what I'm going to write is not going to make any sense, but don't worry about it. It's going to be what I wrote earlier, but it's going to be ill-defined for obvious reasons. Minus t d v. So I have a potential v again from r n plus 1 to r positive. Okay, so this is v x little x dx, and then my old GFF at x. Okay, so all of that is kind of the old definition. I just multiplied my old measure by this radon-Nikin derivative. So I said there's some problems here, okay? So maybe one problem you might see is, okay, well, it's the same kind of thing. I want t to be infinite, right? I want to keep my invariance to the point with the Euclidean transformations. So maybe the first problem, which is not a big problem, it's a relatively not big problem, is I need to take t to infinity, okay? No, sure, whatever. The bigger problem is I don't know if you noticed this. So we had a not long discussion about how x is not a function, right? So x of x doesn't actually make any sense. So x of x is not defined. Okay, but that's not that's not too bad. Okay. So what I'm gonna do is I actually have a few options. Okay, so maybe I'll write solutions. One is, okay, well, even though x is not a distribution, I can smear it out with a smoothing kernel. So maybe let like rho of epsilon be a smoothing kernel. Okay, define define the mu of epsilon to be the old mu, but convolved with I rather want to take x and of epsilon and I convolve it with this kind of smoothing kernel. Okay, so x epsilon is defined because it's a function now, and I can define mu epsilon t just by the same definition, but I put epsilons here. Okay, so now this is well-defined. This is a well-defined probability measure. This should be mu epsilon here. Okay, and then I need to take epsilon t to epsilon 0 t to infinity, right? Okay, so this works. This sort of works. There's a few issues with this. Okay, one is when you smear things out. Well, rho will be like some kind of rotationally invariant smoothing kernel, some like symmetric in every way. So when I do this, you can kind of imagine that kind of smoothing things out in this rotational way, it doesn't interact very well with reflections. So what this means is that this x epsilon here, this is not reflection positive, okay? This is not reflection positive. So the limit should be reflection positive, but it's not so clear how to do that, right? Typically, the way you might want to show a limit has a property is you write it as a limit of some pre-limiting thing, and the pre-limiting thing has a property you want, and the property survives in the limit. But that's not the case here. So there's an issue here. Maybe one technical fix is that you convolve it in all but one dimensions. That way you have reflection positivity in one dimension, and the limit you'll have Euclidean invariance. You can rotate that hyperplane wherever you want, and then you've reflection positivity everywhere. That's a fix. It's a bit technical, but you can do this. Another fix, and this is the one I'm going to focus on more, is you go to a lattice. So you're going to look at, in fact, not just a lattice, I'll look at the discrete torus. So torus n+1, what is going to be? It's going to be epsilon z n+1 intersect with some compact region minus m n+1, okay? So if you do things in this way, now I have actually a discrete finite dimensional space, okay? So I can write down the analog of this Gaussian free field. It's just going to be a random vector now, actually, because this is a finite space. This is a finite state space. I can write down the laws explicitly. I can define this very explicitly as well. So I can define, again, like a new epsilon. Maybe I wrote m here, so I'll keep m here. I can define this well and good. A nice property of this is that lattices, I can flip stuff on a lattice. That's fine. So this thing actually, this is a reflection positive, right? And also you can transit lattices. So it's translation invariant. So it's translation invariant. You do lose something here though, because you can't really rotate the lattice. So you don't have rotational invariance. But you have almost everything, right? Which is basically good enough usually. Yeah, so you have reflection positivity in a couple of directions. Yeah, yeah. So you don't quite have everything. It's not perfect, okay? Um, I I can say, okay, so I'll do a little bit of a historical thing. Actually, I should also say very quickly. Okay, so these are the solutions. I'll say how far you can get with the solutions, and it depends strongly on the dimension you pick, actually. So I guess question is, for what V does these solutions work? These solutions work. Okay. Let me just let D equals n plus 1 for a second. Okay. So for D equals to 2, for D equals 2, basically most things work. Actually, I guess D equals 1 is the easiest. D equals 1, yeah, I guess every V works. This is like quantum mechanics, so this is pretty chill. D equals 2. Okay, so you can do like V, which is V is something bounded below always, so it'll be like polynomials which are bounded from below, exponentials bounded from below, like trig, that kind of stuff. I stuff that you know pretty well. But that's what people can do, at least. Okay? D equals 3. You can do this guy, x to the power 4. Or like other quartic polynomials that are bounded below, which are all basically x to the power 4, in my opinion. They're all basically x to the power 4, all quartic. Okay, really, I mean quartic polynomials bounded below. This is what people can do. Okay. Okay. And D equals 4. Good luck, guys. So no, but you can do, the fact that you can do something, by the way, I should say V of x equals x to the power 4 is like the first like non-trivial thing you can try. Because if you pick V of x equals x squared, now I can't prove it for you here, but all that does is it corresponds to changing the mass m in my Gaussian free field. So it's not really a very interesting change. You don't want to do x cubed, because x cubed blows up. There's an extra singularity. It causes you a lot of extra problems if you do x cubed. So you want to, in general, avoid functions that are not bounded from below. So then the next polynomial you can pick that's bounded from below is x to the 4, right? So this is kind of the first non-trivial thing you try, because you don't want x to the cubed, okay? So this fun.
Is it n plus 1?
Yes. Yeah. But okay. So phi 4, 3. This corresponds to I guess phi for D. This corresponds to the choice of V of x equals x to the 4 in RD, which is n plus 1, as you said. RD. Okay. So now a little bit of history, okay? So these techniques all involve some kind of discretizing or smoothing and renormalization to get something here, okay? And now when you do this, understandably, when you take a distribution evaluated point, you can get some kind of blow up here. But this partition function, this normalization will save you. So you have different blow ups and they're going to cancel out and they'll save you, is the hope, right? And hopefully you can kind of figure out which things are blowing up as you're taking your approximation better and better and better, okay? So I'll say D equals 2, everything's kind of solved. But okay, 5, 4, 2, this was done in like 70s. Okay, 5, 4, 3. I'll say this is done in like also the 70s and 80s by I guess there's a lot of people, Glenn, Jeffy. There's a lot of people that work on this stuff here. Okay, so this is kind of the interesting thing. It's like the kind of really non-trivial thing you can do. And this is probably very hard. The techniques are very difficult. Something about cluster expansion. I have no idea what this is, by the way. But I was told that the techniques here are very specific to the model. They don't apply to other models. But Glenn and Jaffe, they're a textbook. So if you want to read a 1,000 page textbook. You can figure this out and then explain to me afterwards. But these techniques are hard. And the fact that this is the first non-trivial example you can do. So they constructed this and they showed it had the properties. So they completely kind of figured this out. But it was so hard, they couldn't do anything else. And the field kind of maybe died a little bit, right? So that was the state of the field like 30 years ago, is that they did this and then they kind of gave up, okay? But now there's kind of a resurgence in the field. And that's because the techniques which are horrible here, you can actually approach them with some SPDE techniques. So the last 5 minutes, I want to talk a little bit about some SPDE stuff. Okay? So it's going to be sort of a dynamical way of constructing these measures new, okay? So I'll say this talk, the reason why I know about this material is because I attended a summer school on this topic, which is called stochastic quantization, which is this new technique of constructing these measures new. The entire 2 weeks was us constructing 543. Took us 3 hours of lectures and 3 hours of tutorial every single day for 2 weeks. And then we ended up not being able to finish 543. But it's still not easy with these techniques. But it's in comparison, the techniques are more applicable to other models. And that's why this is somewhat interesting. So stochastic quantization. And the idea is it's a dynamical approach to constructing new. Okay, so what I mean is, okay, so let's say this is the measure nu you want, okay? This is some any measure here. What's going to happen is, there are certain measures I like a lot. For example, I like Gaussians a lot. So let's say this, I have some kind of Gaussian measure here, okay? So a Gaussian random measure. Something I understand very well, okay? And what I want to do is, given some underlying Gaussian noise, I'm going to run some kind of dynamics, okay? These dynamics, I'll say a little bit later, are going to be SPDEs, but add for some kind of dynamics here, okay? It'll be dynamics driven by this Gaussian white noise psi here, okay? And this will give me back the measure I want, which is just, so I want this nu to be the push forward of my Gaussian measure, okay? And so I can do this, for a lot of measures. In particular, I can do this for the Gaussian free field, okay? So, this dynamics, what I'm going to do is I'm going to add in, I'm going to add one more dimension, because I like more dimensions, add in a fictitious time t, okay? Okay, so this is fictitious. So this is not my spatial. This is not part of the n+1. This is another whole dimension, okay? Okay, and I'm going to define the following dynamics. Okay, so I'm going to write down an SPDE now, and we'll pretend it makes sense, okay? So dxt is going to equal the Laplacian minus m squared xt plus some kind of driving white noise psi t, okay? So this here, okay, this is going to be, so xt, for any fixed t, this is going to be some kind of Schwartz function of Rn+1. So in particular, the whole process xt for t and r, this is going to be, I guess, R positive cross S Rn+1. So I've added an extra dimension here. And this particular SPDE, which, again, I'll say this, okay, this is some kind of dynamics. I've told you how to construct some kind of dynamics through some white noise here. But this SPDE here satisfies the following, okay? But look at x at any time t, this exactly corresponds to my Gaussian free field measure mu, which is the Gaussian free field of mass m. Okay, so I kind of translated the problem a little bit. Okay, so before I started with mu, okay, my measure, I added in one more extra dimension, this time dimension here, and I have some kind of weird dynamics. Okay, and this dynamics, it mixes things around. So I have some underlying noise, but these dynamics mix around depending on what the noise is. But even though it mixes everything around, at every time t, I still get back a Gaussian free field. Okay, So in particular, the Gaussian free field mu, this is the stationary measure. Of these dynamics, yeah. Okay. So instead of looking at a measure, I pretend that measures the stationary measure of some dynamics, and study the dynamics instead. Okay. How this will help us? I'll show you how you can use this for 5, 4, 5, 4, 3.
I'm just curious, why do you write little d instead of like d by dt or something like that? What does it mean, this little d?
Little d? Oh, it's a good question. I mean, okay, so
How should I think? I understand that it's a stochastic.
yeah.
Is it differentiation in t or not?
It's not. It's not quite a well-defined object on its own. It's not quite a derivative. I'll say this psi is like extremely irregular. So what noise? So this process here is going to be extremely rough. It's going to be nowhere differentiable. So I'm going to take 2 derivatives of it, of course, and then that will be the time derivative. So the time derivative of this nowhere differentiable object is going to be involve 2 space derivatives of it. So I'm taking derivatives of very singular things.
I understand, it's supposed to be a time.
Yeah. So it's a time derivative in the following sense, where if I discretize time, so if I look at like, let's say everything is now discrete, and now this is some process on like z or something, or epsilon z or something, and I look at xt minus xt, and maybe it's like tn minus tn minus 1, so kind of like increments of this, and I look at tn. Okay, so this is like kind of like doing an integral. Okay, so this is like my dx t at n sort of thing. So this is like a Riemann integral, right? And the key thing is that this converges in L2 to to what I call f of xt dxt, okay? But this dxt doesn't really make sense on its own, but it's just sort of how we write it, okay? But it's not actually.
Basically, you're thinking of this as like it's like an ODE for the process. The process is changing in this time.
It's like a PDE, yeah, because it's basically a wave equation, right? There's a, sorry, is this, no, it's not, it's only one time derivative. One time derivative and 2 space derivatives. What is that? A heat equation. It's a heat equation, thank you. But yeah, something like that, right? But this.
You're saying that it's like the process is varying.
Yes, it's varying.
Right, but at every fixed t, it is a Gaussian free
Yes.
But I mean, what is changing then?
So in some sense, it's kind of like I've coupled a bunch of Gaussian free fields together. So at every time index, I have a different Gaussian free field. They have a joint distribution together. So if you know one Gaussian free field at one time, that tells you something about the Gaussian free field at a later time. So it's actually a more complicated process overall. I've kind of added extra layers of complexity. So it seems like I've done extra work, right? But the real key advantage is that my source of randomness is much simpler. I just have a Gaussian noise. This guy I understand extremely well. So the difficulty of the problem has shifted from constructing the measure nu directly to making sense of these dynamics f. Okay, so now I work with Gaussians instead of whatever. But these functions f are going to be complicated. There's a lot of way to define this precisely. This particular one isn't as hard to define precisely, but the moment you make some changes, things are going to get harder, right? Okay, so I'm almost done. I'll finish in like a few minutes, and then you guys can yeah. Oh, so yeah, so f is going to be, it's going to take the noise, it's going to run the dynamics, and then it's going to evaluate at any particular time 0. That's going to be f. Okay. So yeah, so I guess f, maybe, how do I say this? I'll do a little box here. F is equal to x is 0.
CT is Gaussian noise in the
sorry, maybe I should write C. This is like in Rn plus 1. But this is a Gaussian white noise in Rn plus 1. I didn't find a subject, so you shouldn't know what it is, but I can talk a little more later. But Yes, I added another dimension. Yes, yes, yes. Okay. Again, I can talk a little more later, but like defining this stuff is it's not super simple. Yeah.
Claim that the Gaussian free field satisfies this equation and is.
So I can define, I can define dynamics in this way. And it so happens that this dynamics has a stationary measure. That stationary measure is exactly the Gaussian free field. So instead of constructing the Gaussian free field directly, maybe via some kind of limit or something else, I could have constructed the dynamics directly. And I could have just gotten my Gaussian free field by looking at the measure of my dynamics at any particular time, like time 0, for example. Right? So this is like f is equal to x naught, where x naught depends on my noise.
So the property of mean GFF is preserved by this equation.
Yeah. So if you
There's correlations at different time t slices.
yeah, so exactly. So
Capture all the information.
good. Yes, exactly. Okay. All right. So let's say we do our Gaussian perturbation. Okay. So I guess question is, what is the dynamics for my perturbation nu of t? Okay. And the answer, or maybe I'll write nu for now. Okay. The answer is that it's going to be this. Okay, so the dynamics is going to be similar. I'm going to write a very ill-defined thing, but it's going to look very similar. So dxt is equal to the same first term, Laplacian minus m squared xt. Now I'm going to take my temper distribution. I'm going to cube it, of course, and then I'm going to same notes. Okay, so I just kind of add in this cubic term. I guess more generally, it will be v prime of xt, which is like a cubic for x power 4. Okay. So I'll write xt cubed for now to be more explicit. Okay, so minus. Let's plus or minus for now. The technical difficulties are still there, but it is important which one you pick. For those of you that know probability, you can kind of see this via Grossenov's theorem, if you know what that is. So this is just like really Grossenov's theorem, etc. So I'll put like tildes here to say make it clear this is a different dynamics. Okay, so if you can define this precisely, then x tilde t has stationary measure, which is nu. So if I can define this dynamics, very good, right? I'm pretty happy. Now, of course, I have a distribution. I'm going to cube it. Things going to be very singular, right? I don't like cubing these things. So I really need to do some kind of approximation again. Either I go to a lattice or I smear things out and make things into functions. But in particular, I'm going to have to do something there. Things are going to blow up. So I'm going to need to subtract off infinity from this equation to make any sense of it, okay? And this subtracting off minus infinity, let me just say that this is very hard. Okay. So, back when these fluid dynamics PDEs, people worked on this stuff, I believe they knew what this SPDE was, but they didn't know way of properly defining it, because to get this minus infinity is super hard, right? But really, since 2014, there's a big event. A Fields Medal was given for SPDEs. So I guess due to new techniques. Okay. So like example, like Martin Heyer's 2014 work, or like this one has a few authors. One is Guminelli and a few others. This is maybe a 13. Maybe it's 13 or 12. I'm not entirely sure, but we have new techniques to determine what minus infinity is. Okay, so because you're gonna go to some limit. Minus infinity is going to be actually some kind of weird function blowing up. This is going to be some kind of function which is a function positive and Euclidean invariant and is blowing up. So you need to figure out what function to subtract off. That's your minus infinity. But these techniques here give you more standardized tech tools. So here you have like what is called like regularity structures, which You can read a 100-page PDF. Maybe that's how long it is. I don't know exactly, but roughly you read a 100-page PDF and you understand this, or you do para-control calculus, which is not as hard to understand. But basically, you have new machinery for hitting this problem. Okay, so this is giving people a completely new approach, and these approaches are a bit more standardized and they're not as model specific. So that's why a lot of new developments, or at least a lot of new research to be done in this field, and that's why this Euclidean quantum field theory is no longer quite dead. Okay, but I want to like be real with you guys. I want to tell you guys what is new, what people can do. I don't want to claim that this solves all the difficulties of what people had before. The problem was always hard before. Now it's still hard, but the hope is that it might be not as hard as before. Okay. But again, to do this in 543, we try to do this in a 2-week summer school of 6 hours of lectures a day, and we didn't get there. But you get the idea after like lecture 5 or something. Hauschet and Max Gubinelli. I'll also bring on
Does this approach, looking at this SPDE, does it have good properties with respect to reflection positivity? Does it preserve that? Or does it, what is in what way is this helpful?
Yeah. These are really good questions, right? So current research. Okay, so I guess with this new dynamical approach, stochastic quantization, okay? And everything I'm saying is like within a year old, so maybe in the last year everything's changed and it's blowing up. I couldn't do it in a quick search. I didn't find anything last year, but it's possible everything's changed. Okay. So what you can say, so you know how 543 was done completely and all the properties was shown 4 years ago? We can almost do that again now. 543, I guess you can construct it and you can show it almost has all the properties. And the issue really comes to the fact that, okay, first, if you have a solution to this, is the solution unique? You have no idea. It's very hard to show it's unique at all. And so, people, when they want to show something as a property, again, the way they do it is they show a pre-limiting version that has a property and that survives in a limit, okay? Earlier, I gave you 2 examples. I gave you like a lattice limit, and I gave you this convolutional limit. The convolutional limit had my Euclidean notation stuff, but didn't have the rotation or reflection positivity. The lattice one had the reflection positivity and the Euclidean invariant, but it didn't have the rotation. So, really the 2 limits should be the same. That's open. As of a year ago, this is open, and I didn't find a proof within the last year. So that's still open. So not on the 543 side, we're not quite caught up to where we were 40 years ago. But definitely like the dynamics. So XT, like the actual dynamics is new, right? I guess the rigorous definition of, I guess, where stars is SPDE. This is new, okay? And the key thing as well, these properties aren't as model specific. So they apply these kind of regularity structure, para-control calculus arguments to Yang-Mills theory. I'm not going to go into this so much, but you can do Yang-Mills, and so D equals 2. You can do everything you want. In the sense that you can make so Yang-Mills, lattice Yang-Mills is some kind of measure on configurations of a lattice, and you want to take a limit of that. If you do D is a dimensional lattice. If you do D equals 4, they'll give you a lot of money, and it feels metal because it's a millennial problem. But 4 is very hard. So D equals 2 they can do with these techniques. Okay, and in the last year or so, D equals 3. There is some progress. Okay, in the sense that they can show XT, this kind of XT, it'll be a different SPDE for Yang-Mills, but XT for T and R will be defined locally in time and space, right? So what I mean precisely is you see you don't quite have a global solution that exists in all of Rn+1, but you can make it work on a really small section. So these local solutions, you want a global solution, and then you want the law of the global solution, and you have your Yang-Mills 3D. We have a local one, but this is like 24 maybe. There's a few authors, Shen, Hire. I'll write a few more, but there's a few people. This is pretty recent work. So d equals 4 is the one you want to do. But that's nothing. Okay, anyway, that's like kind of the state of the field. There's a few more models you can do that are kind of similar to 543, a few other perturbations. There's like I'll write here, just like sine Gordon or something. And then there's like fractional Laplacians you can do. There's a few small variations, fractional Laplacians. But again, a key thing is that this is not as model specific as the old method. So that's why a lot of people are really excited about these methods. Okay, that's thank you for bearing with my talk. I hope you all enjoyed. Feel free to ask any questions.